In this video, we will see how to count leaf nodes and non-leaf nodes, or the nodes with a degree 0, nodes with a degree 1, or nodes with a degree 2. See, for this example tree, these are leaf nodes, right? These are leaf nodes, and these are all non-leaf nodes. So these are with a degree 0, so these are leaf nodes, and degree more than 0, they are non-leaf nodes. And these are with a degree 2, this is degree 2, right? And this is degree 2. And these nodes are with a degree 1, this is 1, right? And this 1. So that's what we want to count them. We have already seen a recursive function for counting the number of nodes, and this was the function. Already I have shown you the tracing of this one. Now in the same function, if I modify, make some changes, I can count leaf nodes. So let us make changes for various types of nodes. So first one is leaf nodes. See, when do you say a node is leaf nodes? If left child is null and right child is null. So I will remove this line. Okay, I'll remove this line, and here I will say if nodes left child is null as well as right child is null. So P's L child is equals to null if it is null, as well as P's R child, right, is equals to null. Then if both are null, then I will count that node. So I will return x plus y plus 1. Otherwise, means if any one of the condition fails, then it will not enter here. Then what I should return? I should return x plus y. That's all. See, if these are true, then add 1. Otherwise, don't add 1. So it will add 1 only for those nodes whose both left and right child are null. So this will be counting leaf nodes. And after this, if we can return 0, means if a node is null, return 0. So this is already there, we have already seen it. So just by adding one condition in the same function for count, we can change this function for counting leaf nodes. So leaf nodes are with a degree 0. So this function is for counting nodes with a degree 0. Next is counting nodes with a degree 2. So what changes I have to do? So inside this function, I should say P's left child is not equal to null, and P's right child is also not equal to null. If both are not null, then these are nodes with a degree 2. So this node or this node or this node. So for this tree, I will get the result as a 3. There are 3 nodes with a degree 2. This is for finding nodes with a degree 2. So just change of condition, that is sufficient. So if this is true, both left child and right child, both are there, count. Otherwise, don't count. Then third one, counting nodes with a degree 2 as well as 1. Means if a node is having any one child, count it. Means this node should be counted, because this is null but this is not null. This is not null, this is null. Both are not null. So for that, I simply have to change this condition as OR. Now this works for counting nodes with a degree 1 and 2. So all internal nodes. So that's it. This is sufficient. Now next I will show you how to write the condition for counting those nodes whose degree is 1. So only it's a matter of changing the condition. So I will remove this function, and here I will write down all the conditions for leaf node, non-leaf node, all the conditions I will write down. So let us see the conditions. See, first one, leaf node condition. So leaf node condition, if a P's left child, right, is equal to null. So for that I can write not, as well as P's right child should be equal to null. So for that I can write not. This is for leaf node. And node with the degree 2, degree 2. So here condition is if P's L child is not equal to null. So I don't have to write anything. So it is not equal to null only. We have already learned about this one, right? The next is P's R child. If both are true, then this is for degree 2, degree 2. Then the third one, degree 1 or 2. So for this, the condition is if P's left child is not null or P's right child is not null. This is the condition. This is for exactly degree 0, right? Exactly degree 2. This is 2 or 1. Then last one, exactly degree 1. So exactly degree 1 means if it is not having left child, it must have right child. Or if it is having left child, it should not have right child. This is the condition. So for that, I will write down the condition here. That is fourth condition for degree exactly 1. So the condition is if P's L child, right, is not equal to null, then and definitely P's R child should be equal to null. Right? This is one condition. So I'll put it in bracket. Or the second part, or if a P's left child is null, then this should not be null. So I will write down, in the next line I will write down, P's L child is equal to null. See, earlier we have written not equal to null. Here I have written not equal to null. So now it is equal to null. And P's R child should not be equal to null, right? R child not equal to null. This is how we can write on the condition for exactly one child, that is degree 1. See, this is too much lengthy. Can't we reduce the size? See, this is very lengthy condition. This is the continuation from here to here as a single condition. This also should be in the bracket. This is very lengthy. Can't we reduce it? So I'll remove this and show you how I can reduce this one. So this you can take it, if you want to note down, you can note down this one, right? This one I will write once again. This one is just like if left child is there, then right child should not be there, right? This part. Or if left child is not there, right child must be there. Left child is not there, right child must be there. So what is this? This is nothing but L exclusive or L exclusive or and R. So this is with left and right are exclusive or. So is there any exclusive or operation in C, C++, right, like languages? Yes, they have. What is that? So I will write down this condition once again here. So here, if P's L child, right, is not equal to null, this is L, XOR P's R child not equal to null, this is R. Yes, this caps is a symbol used for exclusive OR. So I have reduced this lengthy condition into a simple condition like this. So this is the condition for degree 1. So that's all. We have finished with all various type of conditions. Now count function I have shown you by using x and y variables. It can also be written without using those variables. So it can be written in a simple form also. So I will show you the other ways how you can write down the same recursive function only. So I'll write down the function. See, function name is count. So I will call it as count only, which is taking a pointer to a node, struct node pointer P. See, I will not take any variables x and y. Simply first I will check the condition. If P is equal to null, means if it is null, we know well that if it is null, then return 0. Okay, this is over. Else I don't have to write, because inside the condition there is a return statement. So if it is true, it will return, function will stop, it will never come here. So I can write down the code without writing else. So let us see. Just say return count P's L child, right, plus count P's R child plus 1. That's all. This is so simple. See, left child, right child plus 1. Earlier I was taking these values in x and y variables, then I was adding 1. So now it can be written directly. I am calling the function and the right child also calling the function plus 1. So the working will be same. So this is another way you can write on this one. Then regarding leaf node, non-leaf node, here I should have a condition. That is, if it is a leaf node condition, plus 1. Otherwise, one more time I should write down count left, right, and without writing plus I should write down. See, for example, here I will write if P L child and P R child, not. So this is for leaf node condition. Add 1. Otherwise, return count P's left child plus count P's right child. That's all. So this is the count function. So we have learned how to find the number of leaf nodes and the number of non-leaf nodes. So you can practice this program.